2020. Very good afternoon, everyone. We are going to start our webinar for this week. And today we are absolutely delighted to have our Pro-Vice Chancellor, Professor Bob Nichol, to answer this pressing question. Have you ever wondered why the sky at night is dark? I have wondered, but I have no idea. So Professor Nichol is going to explain. For those of you who do not know Bob, I guess everybody does, but just in case, Bob, after studying at the University of Edinburgh and starting his professional career in the US, at Southwestern University and the University of Chicago in particular, he came back to the UK and chose the University of Portsmouth. Of course, he then became the director of the Institute of Cosmology and Gravitation, and since 2019, he's our Pro-Vice Chancellor. So I'd like to give the floor to Bob for about 15 to 20-minute presentation. Please mute your mic. So Bob, the floor is yours.
Thank you very much, Leila. Maybe can I just say if for some reason I drop out because my teenagers start using the internet, please shout and I'll stop and rewind a bit. Because as soon as I present my presentation, there's a chance I lose my camera, so I probably will not see you. Yes, I thought it would be kind of interesting to give this 20-minute talk about what seems like an obvious question, but has quite some profound implications. And also is sort of partly a review of my own sort of 35-year career as an astronomer, trying to understand some of the more profound questions of our universe. So just to reassure you, I've tried to keep it pretty low on the mathematics, so I won't be showing any equations. I've kept it very physics light, so we won't be expecting you to really understand the details of physics. But I really just want to try and lead you through some of the natural consequences of some of the observations that we've made about the universe. Just to be clear, this isn't a history lesson. Everything I'm going to tell you is based on empirical facts, so things that we can see with either our telescopes or our eyes, and just work you through some of the key concepts about what we can learn about the universe just by looking at it. So again, the area of expertise is observational cosmology, so it's not really about the theoretical side of things, but it's more about what can we know about the universe just by staring through the telescope. So let's go a few slides, if that's okay. And I will start presenting them now, and I'll use them as the sort of basis for my talk. Just to assure you, there's only 4 slides, so I'm not going to kill you through PowerPoint. And if for some reason you can't hear me, please shout out loud, and I'll stop and rewind. So let me just start the presentation. The first slide here that you see in front of you is part of the Hubble Deep Field. So this is one of the most famous images ever taken with the Hubble Space Telescope, which, by the way, is now coming up on its 30th anniversary. So the Space Telescope has been up there now for 30 years, almost my whole career. Really, it's just one tiny part of the night sky, but it's one of the deepest images that we've ever taken. And by that, I mean, we stared at this bit of the sky for many, many days using our most powerful telescopes on the planet. And by staring at this bit of the sky for days and days of time, you can see that most of this image is black. If you stare very, very carefully, you might be able to see there's a few smudges in the background. Those are distant galaxies that you can see. But if you make an estimate of the amount of space or the amount of area that this image, how much of it is truly dark, how much of it is black, how much of it does not have light in it, with an estimate of about 95% of this image is just black. And that's what you see every night if you go out on a very dark night, some of these recent cold nights, that if you go outside with no clouds and you look up, again, you see that most of the night sky is black. And you might ask the question, well, isn't that obvious, Bob? You know, I've known that all my life. Every time I go out and it's good night, at night it is dark. So why am I giving a webinar about something that is just intrinsically obvious to most people? Well, you could ask the question, is that why would it be black if, for example, this is where we start getting into something that is now called Oblers paradox, which is if, for example, the universe was infinite, what I mean by infinite, but it was infinite in both space and time, so the universe had been around forever, and that it extends to infinite size, then you have a situation where in any direction you look in this image, you should in reality find a star or a galaxy. It doesn't really matter which terminology you use. So let's think about that, and a good analogy that we like to think about is if you're in the center of a very dense forest, and look in all directions in a large dense forest, eventually you should see a tree, and there'll be no gaps between those trees. And if the forest is infinite in both time and space, then you should always see a tree no matter where you look. And the same applies to the universe. If the universe is infinite in both space and time, then you would always see a star no matter what direction you look in. So now it becomes quite odd if you think about it. Again, if you believe the universe is infinite in both space and time, it's odd that the universe is actually black. I'm not talking about now our sun here, but when we use our telescopes to look deep into space, why is it that there are empty spaces between the galaxies and the stars that we see? And again, this is Oblers paradox, and really the paradox tells us something about the assumptions that we've just made. And if you just think about it carefully, the assumptions I have made in making my statement is that the universe is infinite in both space and time. And that's not true. Oblers paradox is just a statement that the universe cannot be both infinite in space and time. So by looking at the darkness of the sky, we can make a profound statement about the universe that it's likely that our assumptions are not correct if we assume that the universe is infinite in both space and time. But let's look at this diagram for a little bit longer as we move forward to this century and think about, not this century, sorry, last century moving into this century. If we a little bit more about what this image is telling us, we move into a period of time dominated by a particular character, and that character is Edwin Hubble, whose name was used to name the famous space telescope that shows this image. And really, Edwin Hubble comes to the forefront when we were trying to ask a very simple question about an image like this. This image is two-dimensional, and you can imagine that you can ask a question is, well, how far are the various objects in this image away from us? And I've circled here just two in the image that we know, for example, the blue star-like object at the bottom of the image that I've circled is a star, and we know that now. But if you look at the object in the top left, which is redder and is more fuzzy. And the question at the beginning of last century, which was, were these two objects in the same galaxy? Were these two objects the same distance? Now, just by gazing at these two objects I've identified, you actually assume they are the same. In distance from us, they're roughly the same size. Maybe they're in the same galaxy. Maybe they're within our galaxy. And that profound question really was wrestled by Edwin Hubble and his colleagues by measuring the distance to these fuzzy objects, the thing in the top left-hand side. And he did that through what we call using a standard candle in using objects where we believe we know the brightness of the object, that you can estimate the distance that object is away from us just purely by the ratio of the intrinsic brightness of the object to the apparent brightness of the object. And you do this all the time, your brain does it all the time. When you're looking at a distant light, or you're looking out to ocean and you see a light on a boat, you know that boat is far away because you intrinsically know that's a bright light, and the only way that that light can be dimmer is by putting it further away. So your brain is using this distance law all the time, and we are just using that as astronomers. So interestingly, if you do that and you measure the distance to this fuzzy object in the top left, you see that object is in fact significantly further away than the ghost star that you see at the bottom. And so we now know, we've known for a century, that that fuzzy object in the top left, that red fuzzy object, is another galaxy. And in fact, Immanuel Kant was the first to really postulate that there may be island universes or other galaxies like ours that were out there filled with in space. So this 2D picture now is a little different from the one you first saw, in that the blue object, the star-like object, is close by, it's in our galaxy, but those red objects that you see in the background are much, much further away. They're much brighter than the star, but because they're much further away, they appear to be the same brightness. So now we have a way of measuring distances in the universe, and Hubble was one of the first people to really do that and really figure out that this was a three-dimensional picture, not just a two-dimensional view of the universe. And one step further, about 100 years ago, he made what can only be described as one of the most significant discoveries of the universe, was the universe itself. And I just show you the third slide, which gives you a famous law that he discovered, which is now, for those fuzzy galaxies that you saw on the previous image, he basically plotted their distance from us. This is the implied rate at which they are moving away from us. So on the x-axis here, you've just got a distance from us, and on the y-axis here, you've got the implied speed that we measure that galaxy to be moving at. Now, we measure the speed is just through something called the Doppler effect, which I'm sure you're again all very familiar with, is that moving objects have a different pitch, have a different sound. Well, you're doing that with light now, and therefore the rate at which an object is moving can actually affect the wavelength of light that is emitting. So that's all we're really doing, is we're measuring the change in the wavelength of the light, and that gives you an implied velocity that is on the y-axis. So it's quite a profound plot. It basically shows the further you are away from us, the faster you appear to be moving away from us. So let me just pause there and say that again. This plot, which was made by Hubble over 100 years ago, implies that the further you are away from us, a galaxy further away from us, is moving faster away from us, which is very disturbing. At first sight, when you think about it, you think, well, how does a galaxy further away from us know to move faster away from us based on the distance from us to them? To make up some divine explanation, you could say we're at the center of the universe, and therefore, if we were at the center of the universe, it would make sense that things further away from us are actually moving faster away from us. But it's not the explanation we like. The explanation as scientists we like is to try and find something that is easy and as obvious. We term there's something called an Occam's razor, where we try and understand something that is intrinsically difficult. We try and understand the most straightforward explanation for this particular observation. And what I think is going on here, the explanation for Hubble's famous plot, is the same as if you were doing some baking and you put a cake in the oven, and the oven expands, and as that cake expands, then all the parts of the cake are moving away from each other as that cake expands, with relationship is exactly the same as you see on this graph. In other words, the ends of the cake are moving faster away from each other than, say, chocolate chips that may be in the cake or sultanas that may be in the cake that nearer together are moving. So a very simple explanation for this plot is that space between the galaxies is expanding. And therefore, what we naturally come to is that the universe, this is the discovery that the universe is in fact expanding. So it's no longer static, it's no longer finite, infinite, but by definition, if the universe is expanding, you can turn the clock around, and that then implies that the universe had a beginning. So the plot solves Oblers' paradox in that this tells us that the universe is finite. It had a start, and since that start, it has been expanding, causing the Hubble relationship or the Hubble law, as you see here. So a profound observation. And what was very interesting about this time at the beginning of the last century was that not only was this a profounding observation, but ironically, it was predicted a few years before Hubble made this plot. In fact, the great Einstein had come up with his theory of gravity, and to apply that theory of gravity to the universe as a whole, you actually do predict an expanding universe. So this was a case where actually this particular observation was predicted by Einstein's general relativity before it was observed. And so we had the combination of both a theoretical explanation for this plot, but also the observation itself that proved, one of the first proofs, that general relativity was a good explanation for the universe as a whole. But then you are, if general relativity explains Hubble's diagram, you're then left with the interesting conundrum that general relativity is a theory that combines the contents of the universe, and space and time is affected by the contents of the universe. And it launched, I would say, a whole century of effort where people were very interested in what is the content of the universe, because if we could figure out what's the content of the universe, we could figure out how it would affect space and time, and then we could actually figure out the future of the universe. So we could count all the what all the matter in the universe was, where it was, how it was distributed. You could then use general relativity from Einstein to predict what the future of the universe would look like. So you can imagine, as cosmologists, we were all very excited by that. And when I joined as a cosmologist back in the 80s, we were still struggling with this very concept. What was the content of the universe? How much matter was in the universe? If we could make that measurement, then we could, in theory, predict what the future of the universe would look like. And I'll fast forward to 1999, where we made a major discovery about the universe that really helped decide what the content of the universe was. And using these standard candles again, but no longer the same ones that Hubble was using, but supernova, and this is where my area of research comes in. And by using supernova, we can now measure the distance, not just in our local universe, but half the distance to the Big Bang. We can basically measure half the distance to the end of the observable universe. It allowed us to make this plot, this one that Hubble first made, but we can make it over a much larger, more vast area than that. And what we discovered back at the turn of the century was that the universe was the supernova that we observed were fainter than they should be. So what I mean by that is if we took all the contents of the universe and we predicted what the brightness of these supernovae should be, we discovered they were actually fainter than they should be. And that was quite a conundrum, because there are only two real explanations for why these supernovae should be fainter than they should be. One was we'd done our calculations wrong, Or the other was that they were no longer standard candles, and in fact they were intrinsically different brightnesses across the universe. The answer to that conundrum was that we'd done our calculations wrong, not that these supernovae weren't standard candles. What I mean by we had done our calculations wrong is we had only assumed that the space between us and those supernovae was only warped by matter that we could see between us and the supernova. And in fact, just pure energy, remember the E equals mc squared equation, well, energy has an effective mass and mass has an effective energy. So while we were counting up all the mass between us and the supernova, we included the potential for there to be energy between us and the supernova. And in fact, the answer to this conundrum is, in fact, these supernovae are dimmer because they are further away, and further away not because there is more mass between us and those supernovae, but there's an energy component to the universe that's between us and those supernovae. I'll move on to my last slide just to illustrate what our present knowledge of the universe is. And that is that as the universe has started from the Big Bang, that first moment of conception, illustrated there on the left-hand side, the universe has expanded, as we discussed with Hubble's diagram. But at the end of this trumpet diagram you see on the right, you see that expansion is getting quicker. The universe is getting larger, faster. And that extra expansion that you see at the end is what is the cause for supernova being being dimmer and therefore further away. So it's quite a profound debate, and it leads us to yet another set of questions, as we tend to find. Once you've answered one set of questions, you move on to a set of questions, which is, of course, what is driving this acceleration? Why is the universe expanding quicker today than it did in the past? Our explanation for it today, and this is ongoing research right now, is that accelerated expansion, that reason the trumpet is getting wider as you go into the future, is that there is a component of energy, there's an energy component to the universe that we call the cosmological constant. And this was actually postulated very early on by Einstein himself. But the cosmological constant, we believe, is associated with the space itself. So here's the irony: as you get more space, you get more cosmological constant, which causes the universe to accelerate more, which gives you more space, which gives you more cosmological constant, which causes the universe to expand, and so on and so on. So if the answer to this conundrum is a cosmological constant, actually this trumpet will just get wider and wider, faster and faster, and we'll end up with the universe expanding faster than the speed of light. And we'll get into quite a strange universe far into the future. Just to reassure you, that is a long time in the future. But you could ask the question, why is there a cosmological constant? Why does space have an energy associated with it? And actually, there is a natural explanation for that in another one of the great physical theories about quantum mechanics. But that's another lecture for another day, and I won't go into that. So I can just summarize where we are today. This picture I show you is basically a very good summary of what we think the evolution of the universe was like. That trumpet expands quicker at the end. It's a conundrum we are still dealing with, and astronomers and cosmologists around the world are presently building a new generation of satellites and telescopes to try and really prove the understanding of the cosmological constant that we think is driving that. One of the key questions, of course, is it truly a constant? If we could measure the contribution in different parts of the universe, then maybe we can test the assumption that the cosmological constant is the thing that's driving that expansion. So I've talked for longer than my 20 minutes, so I apologize for that. But hopefully that's a whistle-top tour. Hopefully you heard everything. of why the sky is dark and really brings you up to date on what our thinking is of the expansion history of the universe. Thank you very much.
Thank you so much, Bob. That was really great, really fascinating, I think, for everyone, and easy, I felt, to understand. I just don't know whether I really understood it. And I'm going to use my privilege as a chair to ask the first question. But colleagues, please ask your questions in using the chat banner. You have at the bottom of your screen, you have a place where you can write down your question so that you can see it and ask it to Bob. So the first question as a chair, and again, we'll just wonder whether I'm anything. What are the possible consequences if the universe expands faster than the speed light?
Question. I mean, that is a very good question. One I'm not sure I'm qualified to answer, but I will give you my best shot. Of course, there is also theories that say nothing can go faster than the speed of light. But those are solid objects, you know, those are objects like a table or a spaceship, right? So we know if space can expand faster than the speed of light. We don't know if it will be a consequence of the theories that we've got, because we just simply have never seen anything like that. What's interesting is that if you are interested in learn more about that, there is people that speculate if it does expand faster than the speed of light, what will happen that the fabric of space-time may come apart. So it's like a jumper with the threads sort of being pulled apart, and therefore God knows what that means in terms of our theories of the universe. But from an observational point of view, of course, the galaxies will then be moving apart from each other faster than the speed of light. That doesn't mean they are moving faster than the speed of light. So let's be clear about that. If two galaxies are pulled apart faster than the speed of light, they're themselves not moving faster than the speed of light, so there's no violation there. But the light can't get from one galaxy to the other galaxy because they are being pulled apart faster than the speed of light. So actually what we think is if the universe is moving faster than the speed of expanding faster than the speed of light, the sky will just go dark. You just won't see anything. Because of course the galaxies, that there will not be enough time for light to come to us and for us to see. So it's a depressing picture. The night sky will kind of fade into darkness and it'll be a very empty, lonely place. A bit like today, today. So that's as good as I can do at the moment, Leila. But that was a very good question.
That's great. Thank you so much, Bob. So in the meantime, we had questions. We have one question from our colleague Tarek, who presented last week a very good presentation. I know that the Earth is a tiny part of the universe, but I would be interested to know if this expansion process is affecting the Earth in a way or another, and how.
I'm going to try and find the comments. There we go. So I know it's a tiny part of it, but I would be interested to know if this expansion process. That is an excellent question as well. Interestingly, I asked the question: well, is the space, is the room expanding? Okay. You know, I might suddenly going to get a bathroom that's slightly bigger tomorrow than the one today, and the answer is no, because this expansion is only seen out in deep space from very dense objects like the Earth and dense objects like us. In fact, just to put it into context, the density of matter in the Earth and in the solar system exceeds by many orders of magnitude the density in empty space. The chemical bonds and the forces that hold together the atoms far exceed the strength of those, far exceed the strength of the gravity and the expansion that we're seeing in deep space. So objects like the Earth, objects like the solar system, even objects like our galaxy are bound together by the chemical bonds, by the electromagnetic forces that hold those things together, and we would not experience this expansion in our own local neighborhood. It's only the space between, when we get into the empty deep space, the expansion take over. So don't worry about the room getting bigger.
That's really nice. Colleagues, I'd like to have more questions. I know that some of you are really specialists of these issues or really interested. I have another question in the meantime. I don't know whether it relates, but very recently we had this so-called pink moon, this super big moon. What's it called pink?
There's a common misconception here, Leila, that actually while I am an astronomer, I actually am not that interested, as you can tell, in objects within our own solar system. So I'm going to actually, you can Google that and find that yourself. If there are any questions about things beyond our solar system, I'm more than happy to answer those.
Because I discover also the complexity of the field, and I'm sure you have many subspecialisms.
Absolutely, I wouldn't. You can find that easier on Google.
People, do you have questions or comments? Do you want to take the floor, maybe also, because you may have something to say, something in relation to your own discipline, your research.
And then Leila, if you're looking for questions. Your presentation.
Nice you.
Yeah, how you doing? So just a quick question as to I guess, how confident are you that the observations are accurate? I was struck looking at Hubble's original plot that you had a couple of nice straight lines going through the dots on the graph. And if you took the sort of fastest data point and the slowest far data point, you could have actually drawn a horizontal line. So the modern observations give you complete confidence that that what you're talking about is accurate.
I mean, I'd show you Hubble's diagram because historically it's the one that really kicked off the whole field. One could argue cosmology started with Hubble's diagram because before that we didn't even feel there was an external universe that we wanted to explore. So that's the historical context of why we showed that, or why I showed that. The modern version of Hubble's diagram is exceptional. I mean, it is beyond reproach. There are, for example, in terms of the sort of supernova events that we talked about in terms of the standard candles, there are now thousands of different points. But also, it's not just the number. Each one of those data points has now been observed and refined and improved to the point that there is very little scatter around that line. So the modern experiments, which I'm more than happy to share with you offline, Adrian, are beyond reproach. But I think the reason I'm so confident is, of course, many scientists, we haven't just used one way of measuring it. There are multiple ways now in which we measured the expansion of the universe. There's the famous cosmic microwave background that we should mention. So there are many, many bits of information that the only rational explanation when you put all those bits of information together is that we live in an expanding universe, and that expansion is increasing with time. So I would say 99% of cosmologists have now given in to the idea that we live in an ever-expanding, ever-accelerated expanding universe. There's 1 in 100 that is looking for an alternative explanation, and we need people like that will keep questioning. But I would say we are 99%. Which is more than 99% sure, but 99% of cosmologists believe that the observation as shown.
Thank you so much, Bob. And that was our colleague Adrian Hopgood, who's Team Director for Emerging and Future Technology. Marika kindly reminds me that we have special guests today. I think we have a number of friends from the Cafe Scientific or Cafe Science. And we also have friends from the Hampshire Astronomical Group. So a very warm welcome. Thanks for joining us. And if you have questions, please feel free to write them down. I see that we have more questions. There is one from Gary. Gary is asking the following question. Related to the previous question, there is an assumption that the universe is uniform and constants are universally constant. It's absolutely proven. That's quite technical. I like that. And then we have a question. I will answer this one first.
This question is again an extremely good one, and let me take the last bit first about the universality of the constants of we have to. I mean, we have to start by assuming, and I should have been very clear about that. We have to start by assuming what's called the cosmological principle. It assumes what we see locally applies across the universe. So Hubble's law, let's say, for example, Hubble's law that we see from the Earth, we have to assume that that law applies throughout the universe. If we don't, I think we just stop. We simply have to give up, because then the myriad of alternative explanations becomes hard to cope with. So the basic principle basically says the laws of physics that we see here today apply across the universe. So the electromagnetic law that we use to power our computers is the same as would be the same here as on the other side of the universe. The same about gravity. The gravity that causes the moon to go around the Earth is exactly the same gravity as applies, billions of light years into the future and into the past. If we assume that, we have no way of making progress, because then you could say, well, the laws of physics are different over here than over there. And you say, well, how different are they? Well, they're very different. Oh, well, then, what? So suddenly you just get an infinite number of opportunities and solutions, and you would never make any progress. So you're right. We do assume the constants are universal. Has that been tested? It's extremely difficult to test that, because, of course, as you're trying to test the constant, you are also making these observations about the expansion of the universe, the contents of the universe, and things like that. So you're trying to hold one thing secure while changing that. If you want to change that, then you can't change this as well. So it becomes, again, extremely complicated if you start letting everything change in the universe. But there are some people who really are trying to test that, and there are some interesting observations, I would say, done by some colleagues in Australia that look at the chemical composition of very distant objects, or distant quasars, the chemical compositions of those, and look at the some of the transitions within the spectra of those quasars, and actually can show that even these distant objects seem to follow the same physical laws as the nearby objects. And therefore, again, that's sort of an indirect test that the chemistry of these very, very distant objects is the same as the chemistry that we see today. And that, again, is an indirect observation that those distant objects look to have the same chemistry as we have on the planet. So that really, again, sort of seems to demonstrate that the cosmological principle assumes. The question about if the universe is uniform, the answer is we think so. There are observations of the cosmic microwave background that seem to indicate that it's uniform to a very high precision, although that was challenged in the last week or two. And I don't know if people saw the press releases that came out about potentially there being some asymmetry to the universe. It is got to be very small. There could be something there, but it's got to be very, very small, unless it would ruin the observations of the cosmic microwave background. But something we will test in the years to come. So one thing we are definitely interested in testing is if the universe is homogeneous and isotropic. And the next generation of experiments should be able to test that very question posed there. So thank you, Gary. That is an excellent question. It is active research at the moment.
I think we have a question which might relate from Lou. She says, are two methods for determining the cosmological constants which give consistently different values. Can you explain?
I'm going to guess Lou is not talking about the cosmological constant, but Hubble's constant. If he is talking about that, then I'll give you my thoughts about that. I just want to make sure that Lou is referring to Hubble's constant. That is the slope of that line. So the line I showed you from Hubble, the slope of that is quite an interesting measurement in itself. And where that line hits today, Lou, okay, hey, it's amazing how interactive this is. So the way that where that line hits the y-axis, so the value of the slope today is called Hubble's constant. Who is right? There is now again what we call there is a conflict there between the measurements of that Hubble's constant based on different measurements. There are ones where you start the measurement today and work out, or you start the measurement far away and work backwards. So if you start here and work backwards, you get a value like that. If you start here and work outwards, you get a value like that, and there's a gap. The existence of that gap today is pretty significant. I'd say most cosmologists now are getting quite worried that the methods of measuring this constant are disagreeing by quite a significant amount. So there are two options for why there is a significant difference. Either one of those measurements is wrong, and cosmology has a history of making measurements, not because of people being bad scientists. It is just a very, very difficult thing to do. That the measurements, one of those measurements is wrong. Which is probably more intriguing is that it may be evidence that our theory of the universe on general relativity is not the full explanation for the expansion of the universe. And one possibility, just to come back to the previous experiment, is that when you make that measurement and you see the gap, we've only done that in certain parts of the universe. So we've only just sort of done it over there and we've done it over there. If the universe is non-uniform, then we get different measurements of the Hubble constant based upon whether that part of the universe is slightly different from that part of the universe over there. So one of the intriguing things about that measurement maybe is it tells us maybe the first glimpse that the universe is not as uniform, not as homogeneous as we first expected.
Excellent. Thanks so much, Bob. We have a question from Chris. The second law of thermodynamics suggests energy is being lost. So how can the energy of space be increased?
Sorry, who is that?
From Chris.
Chris, that's an extremely good question. So they are different. So just so I'm clear, the thermodynamics right is that you would expect energy to be lost, but energy is not the same energy as associated with the empty space and time. So here, what we believe is happening is the cosmological constant, which is the energy associated with space itself, is due to quantum fluctuations that are going on within that empty space-time, whereas the second law of thermodynamics is the energy associated with hot radiating objects that don't necessarily have to lose the energy, for example. So the energy is given out, that is reabsorbed, say, as the star is emitting more energy, that energy can be absorbed by other things in the universe and be processed, whereas the energy within this within the cosmological constant is associated with we think the quantum fluctuations within that box of space-time. So they're different energy sources, the one is not related to the other. Does that make sense? It's an extremely good question, probably beyond today's presentation.
We do have another quite provocative question from Anonymous from Twitter. And the question is basically, why are we spending so much money on that while we know that we have more pressing issues to tackle, and climate change in particular? Well, yes, there are implications anyway.
So this, it's a fair question. It's a fair question. It's a terrible time we find ourselves. Why shouldn't we all be spending the money on more direct and meaningful, let's say, contributions to society? I kind of would like to answer that question two ways. So the first way I would like to answer that question is, we are human, we are inquisitive, we are curious, and we have an insane drive to understand the world around us. You cannot stop people asking questions like, where are we coming from? What's the future of the universe? What is our future? And we are just inquisitive beings. And I think if we stop asking these profound questions, I'm worried that we are no longer human. It is a human trait for us to ask these big, profound questions, and then, try and understand what those profound questions are for the sake of humanity. I think that is, again, it sort of defines that we are different from any other species on this planet. I'm assuming the dolphins and not asking these profound questions. Maybe they are, but it is what makes us human. We ask these profound questions and we want to seek answers for these profound questions. So I make no apology for that. It is, I think, what makes us human and what makes us different from other species. Then say, while we are searching those profound answers, we accidentally trip over some very, very useful discoveries. And the one I like to always point to is the camera we are using right now in all of our laptops, in all of our phones. That technology you are using was driven by astronomers. The desire to make digital images of the night sky, the desire to observe the universe, to see what's out there, has led to digital technology that we are using right now in our video conference. So I'm not claiming that astronomers created video conferencing, but the initial desire to have digital detectors was driven by the desire to observe the universe. So there are profound consequences and applied consequences to us having the to do astronomy and physics in general. I don't know if that convinced you, but that's my answer to your question.
I think for the very same reason, we still give money to philosophers, historians, and you name it, because we have profound questions to answer. We have excellent new questions here. I see three. One from our colleague Sam Robson. Can you use the chemical profiles generated from distant galaxies to create a kind of phylogeny of galaxies, showing which have more similar chemical structure to one another? In the expanding universe, one would expect closer galaxies to have come from a similar source and therefore show similar chemical profiles.
Yes, excellent question, Sam. And yes, you are right. There's a whole branch of astrophysics looking at the chemical composition of galaxies and trying to understand how chemistry came about. So if you're interested in that, I would actually say there's a colleague of ours that you could ask, Claudia Mariston, who could come on and actually explain the chemical history of the universe and how the compounds came about. Sort of just, again, another fascinating subject is that, as you're probably aware, at the beginning of the universe, there's only two elements. So the elements that that the universe was made from, at the beginning, the universe only had hydrogen and helium, which are elements of lithium and beryllium and those things. But most of the universe at the beginning, it was hydrogen and helium. So all the other elements, so all the things like gold, iron, all the elements that we take for granted on our planet were actually made through the process of stellar evolution. So stars growing, stars blowing up, producing heavy elements that are then spewed into the universe that then create planets, and then you and I dig those elements out of the ground and we make, wedding rings and we make watches and things of them. So all the elements we see on the Earth today, bar hydrogen and helium, really came from the centers of stars and the explosions of stars that then polluted the universe. At some level, stars pollute the universe with all the heavy elements that you see out there. Everything we've seen, everything about the universe we've measured, says that chemical process is the same throughout the universe. So a distant galaxy seems to be creating its elements in exactly the same process as our galaxy is creating its elements. But I could have a whole long seminar about the chemical processes and the creation of those elements. And I would strongly recommend Claudia Mariston to give you that lecture.
Super. A really profound, I think, question from our colleague Andy. Let me find it. Given the billions of galaxies in our own galaxy and beyond, something I've always struggled to get my head around, where did all the materials, mass come from to create the universe in the first place?
Wow. So that, believe it or not, is another question. But in modern cosmology, the universe started with the Big Bang, and the Big Bang was a moment of energy. And as we know, energy equals mass equals mc squared. So as the universe has expanded and has gone through multiple phases as it's expanded, part of that phase, one of those phases, is the creation of the electrons, the neutrons, the protons that we see today. And the stuff we are made of was made in the Big Bang. There's nothing else. If you believe modern cosmology, it's the universe and nothing else. So the universe created its own matter. There's an extremely good book. If you really want to know, there's a book by Joe Silk called The First 3 Minutes. It's still a fascinating book today, and that describes how in the first 3 minutes of the universe, all matter we see was created. So I strongly recommend you read, because since you're stuck at home with nothing else to do, I'd strongly recommend books, The First 3 Minutes, and that will address that question.
But I have another question from Graham. As the expansion continues, is it where we hear of the Great Rip at the end of the universe?
So if the universe continues to expand, again, we come back to almost the first question where we said, what happens when the universe is expanding faster than the speed of light? Of course, we don't, excuse me, we don't know the answer to that because we've never expanded space faster than the speed of light before. So one postulate is something called the Great Rip, which when the fabric of space-time actually comes apart, and the universe in fact end through what's called the Great Rip. reassure people, if it was ever a great rip, that the expectation is somewhere in the region of 10 to the 60, so that's 10 to the power 60 in the future. So that is billions and billions and billions of years in the future. So you have to keep paying your mortgage. You have to keep, you have to stay inside for the next few weeks. And the last thing you should be worrying about is whether the universe has a great rip or not. But if it does happen, it'll be so far in the future that probably we'll all be, and all our ancestors will be long gone.
But I think that was the last question, basically, Bob. But we're nearing, the end of the seminar, the webinar. That was really absolutely excellent. So thank you so much. Now we can.
Thank you.
Presentation that was really great. I believe that if you have more pressing questions on the universe, you can always ask Bob.
Yeah, you can always ask me on Twitter. So hopefully people can find me on Twitter and send me the question that way.
That's great. We had a great coverage today on Twitter. I'd like to conclude in making a few announcements. Next week, we are going to have Professor Asif Qureshi from Korea University, live from Seoul, to talk about the Americanization of trade. Really interesting. The week after, we have the Director of Trademark East Africa from Nairobi, talking about the future of development aid together with Professor Tamsin Bradley and myself. Then we have our colleague Gordon Bloom, who's the Director for Health and Wellbeing at the university, talking about public policies, public health policies with myself. And then again, we have another colleague, Dr. Henry Pierce, to talk about data privacy in times of pandemic. So lots of really interesting webinar discussion to come. So try to remember on Wednesdays from 2 to 3, you're busy because you're attending the webinars. Thank you so much, everyone, and we'll see you next week. Bye.